Let's talk about the uses of crawling policies. If you plan to create a web crawler, whether for a research project, a class project, or as a personal educational project, you should tread carefully and act thoughtfully. Your crawler may have the potential for disrupting the services of another website, causing extra effort to deal with the invasion of your crawler, or even creating a legal liability for the university. So, there are policies to guide you through the process of creating and maintaining a web crawler. There are two important characteristics of the web that generate a scenario in which web crawling is very difficult. The scenario is its large volume and its rate of change. As there is a huge amount of pages being added, changed or removed every day. Also, network speed has improved less than the current processing speeds and storage capacities. The large volume implies that the crawler can only download a fraction of the web pages within a given time, so it needs to prioritize its downloads. The high rate of change implies that by the time the crawler is downloading the last pages from a site, it is very likely that the new pages have been added to the site, or the pages have been already updated or even deleted. As the bandwidth for conducting crawls is neither infinite or free, it is becoming essential to crawl the web in a not only scalable but efficient way if some reasonable measure of quality or freshness is to be maintained. So, a crawler must carefully choose at each step which pages to visit next. The criteria for this selection are decided by the outcome of a combination of policies. In short, this means that the behavior of a web crawler is guided or settled on a combination of policies. There must be a selection policy that states which pages to download. There must be a revisit policy that states when to check for changes. There must be a politeness policy that states how to avoid overloading websites. And there must be a parallelization policy that states how to coordinate distributed web crawlers. We will now look at them in detail. As for the selection policy, it decides which pages are to be downloaded. Given the current size of the web, even large search engines cover only a portion of the publicly available content. As a crawler always downloads just a fraction of web pages, it is highly desirable that the downloaded fraction contains the most relevant pages, and not just a random sample of the web. A study by Lawrence and Giles in the year 2000 showed that no search engine indexes more than 16% of the web. The process requires a matrix of importance for prioritizing web pages. The importance of a page is a function of its intrinsic quality, its popularity in terms of links or visits, and even its URL. Designing a good selection policy has an added difficulty. It must work with partial information, as the complete set of web pages is not known during the code. Many web experts have studied the policies of schedule planning for web crawling carefully. We will look at a brief description of these studies. In 1998, Cho et al. Conducted the first study on policies for crawling scheduling in which a crawling simulation was done with different strategies. The ordering matrices tested were breadth first, backlink count and partial page rank calculations. One of the conclusions was that if the crawler wants to download pages with high page rank early during the crawling process, then the partial page rank strategy is the better, followed by breadth-first and backlink count. However, these results are for just a single domain. In 2001, Najarak and Wiener performed an actual crawl on as many as 328 million pages with the help of breadth-first ordering. They found that pages with high page rank were captured by the breadth-first crawl. It was concluded that this was due to the fact that most important pages have numerous links attached to them from several hosts, and those links will be found early. Here they did not compare other strategies. In 2003, Abiteboul designed a crawling strategy based on an algorithm called OPIC, meaning Online Page Importance Computation. In OPIC, each page is given an initial sum of cache, which is distributed equally among the pages it points to. It is similar to a PageRank computation, but it is faster and is only done in one step. An OPIC-driven crawler downloads first the pages in the crawling frontier with the higher amount of cache. However, there was no comparison with the other strategies, no experiments in the real web. In 2004, Boldy et al. Conducted a simulation on subsets of the web of 40 million pages from the IT domain and 100 million pages from the web-based crawl, testing web first against a random ordering strategy. The winning strategy was breadth first, although a random ordering also performed surprisingly well. One problem is that the web-based crawl is biased to the crawler used to gather the data. They also showed how bad PageRank calculations carried on partial subgraph of the web. In 2005, Bersisa Yates conducted a simulation on two subsets of the web of 3 million pages from the GR and CL domain, testing several crawling strategies. They showed that both the OPIC strategy and a strategy that uses the length of the per site queues are both better than the breadth-first crawling, and that it is also very effective to use a previous crawl when it is available to guide the current one. Web crawlers aim at accumulating as many resources as possible from a website. They accumulate information by downloading the information. In 2004, Kothi introduced a path extending crawler. This path crawler had the quality to extend to every possible path in the URL. This crawler was considered extremely beneficial in tracing isolated resources. It even found out resources that would not have given on any inbound link in regular